Hello students, welcome. Previously, lesson 2 in the chemistry of the gases, we were dealing with the methods of gas collections. So today, lesson 3, we want to proceed to the first gas, which is oxygen gas. And we are saying, note, oxygen gas is taught in chemistry from 1 to topic 4. And the name of that topic is called chemistry of air and combustion. So we start with laboratory preparation of oxygen gas, and we are saying preparation of oxygen in the laboratory can be done in the following ways or in the following methods. So the first method is called decomposition of hydrogen peroxide in the presence of manganese peroxide as catalyst. So this method is also known as catalytic decomposition of hydrogen peroxide. Okay, this is how the setup for the catalytic decomposition of hydrogen peroxide look like. So here we're having a drop-in funnel. It has a top. Then we're having the hydrogen peroxide. So here we're having a flat bottom flask here containing manganese peroxide. So when hydrogen peroxide decomposes in the presence of manganese peroxide, a colorless gas is produced, and the colorless gas goes through the delivery tube. We have the delivery tube there, and the gas is collected by this method of gas collection called overwater method. So in the overwater method, we're having the gas to collect the oxygen gas, and here we have the beehive shelf here, and this is the trough, and this is the water. So we're saying hydrogen peroxide decomposes slowly to produce oxygen and water under normal conditions. But on adding manganese peroxide, it's manganese peroxide, not manganese 5 oxide. We are told the rate of decomposition is speeded up. Therefore, manganese peroxide acts as a catalyst. So we are saying now, what is a catalyst? And we are saying a catalyst is a substance that alters or that speeds up the rate of a chemical reaction but remains chemically unchanged at the end of the reaction. So for us to write the word question, we're having hydrogen peroxide being decomposed in the presence of manganese peroxide, which is acting as a catalyst, getting or giving us or forming water and oxygen gas as a product. So we're having hydrogen peroxide in chemical symbol, which is in liquid in physical state. We're having a manganese peroxide, which is acting as a catalyst, and we are getting 2 moles of water and also 1 mole of oxygen gas. So this is the chemical equation for the decomposition of hydrogen peroxide. We are saying oxygen is collected of a water method. Reason? Because it is slightly soluble in water. And we are saying the first few bubbles of oxygen are not collected. The reason why we are not collecting is that because the gas is mixed with air, which was originally or initially in the flask. For that reason, we are not collecting the first few bubbles of oxygen gas. So next, we want to proceed to the second method of preparing oxygen gas, and that's called adding water to solid sodium peroxide. Adding water to solid sodium peroxide. So the setup is just the same as that of catalytic decomposition of hydrogen peroxide. The change is only where we were having the drop-in funnel, we have put the hydrogen peroxide initially. So here we put water. Remember, hydrogen peroxide is liquid, water is also liquid. So in the flat bottom flask or in the beaker, there in the catalytic decomposition, we have placed the manganese peroxide, which is a solid. So here we are going to put sodium peroxide. And the gas will go through the delivery tube, and we are going to collect by overwater method. Oxygen gas is collected by overwater method. So that means the two methods, that is catalytic decomposition of hydrogen peroxide and also adding water to solid sodium peroxide, we can use the same setup. But the change will be only when you are dealing with the hydrogen peroxide. The hydrogen peroxide will be in the drop-in funnel. If you are dealing with the next method or the other method, that's adding water to sodium peroxide, in the dropping funnel, we are going to have water. So in the round bottom flask or in the conical flask, in case we use a conical flask, we are going to put manganese peroxide if you have hydrogen peroxide as your liquid. But if you have water as your liquid, we are going to put sodium peroxide in the round bottom flask or in the conical flask or the reaction vessel that we are using. So we are saying sodium peroxide plus water, we are going to get sodium hydroxide and oxygen gas. Let's write the chemical equation. 2 moles of sodium peroxide plus 2 moles of water will give us 4 moles of sodium hydroxide and also 1 mole of oxygen gas. So the third method, or method C, of preparing oxygen gas in the lab is, we are told, heating the following. So if we heat the following, we are going to get oxygen gas. Number 1, or Roman 1 of C, heating potassium manganate 7 crystals. So we're having this setup here. We're having a boiling tube, and this boiling tube is heated, and this boiling tube contains potassium manganate 7 crystals. So when it is heated, we are going to get oxygen gas, which will be collected by our water method. So we're saying potassium manganate 7 decomposes on heating to form potassium manganate 6, manganese 4 oxide, and also oxygen gas. Those are the products that we are going to have when manganese peroxide is heated. So to write the word equation, potassium manganate 7 being heated, we are going to get potassium manganate 6, manganese peroxide, and also oxygen gas. In the chemical equation, we are going to have 2 moles of potassium manganate 7 being heated to decompose to give us 1 mole of manganate 6 crystals, and also we're having manganese peroxide and also oxygen gas. That is heating potassium manganate 7. So Roman 2 of C, heating, we said heating potassium chlorate 5 or potassium chlorate. We use the same setup with that of potassium manganate 7. They are the same. So here we're having potassium chlorate 5 or potassium chlorate being heated. We are going to collect the gas, oxygen gas produced by our water method. So we're saying when potassium chlorate 5 or potassium chlorate is heated, oxygen is evolved. Potassium chloride is left as a residue. So that means the potassium chloride will be left in the boiling tube. So we're saying in this decomposition, manganese peroxide can be added to the potassium chlorate 5 before heating for it to catalyze the reaction. So for manganese peroxide to act as a catalyst and also lower reaction temperatures. So next, let's write the chemical equation for the decomposition of potassium chlorate 5. So 2 moles of potassium chlorate 5, which is solid, being heated, it will give us 2 moles of potassium chloride, which is solid, and 3 moles of oxygen gas. So we proceed to the third heating of sodium nitrate. So here we're having the same setup as that of heating potassium manganese 7 or potassium chlorate 5 and sodium nitrate. They are going to have the same setup, and the oxygen is collected of a water method. And we are saying when sodium nitrate is heated, it decomposes to form sodium nitrite and oxygen gas. So this is the question: sodium nitrate being heated, we are going to get sodium nitrite and also oxygen gas. To write the balanced chemical equation, we are going to have 2 moles of sodium nitrate. When heated, we are going to get 2 moles of sodium nitrite and also 1 mole of oxygen gas. Okay, we will proceed. We go. So the oxygen that we are collecting is wet because we were collecting it of a water method. So we are saying drying of oxygen gas. That will be the next thing that we are going to go. If dry oxygen is required, it should be bubbled through a wash bottle containing concentrated sulfuric acid or passing it through a U-tube containing anhydrous calcium chloride or calcium oxide. Remember, in the lab we said we have 3 drying agents. One is concentrated sulfuric acid, the other one is anhydrous calcium chloride, and the last one is calcium oxide. So if we want to dry oxygen gas, the wet oxygen gas that we have produced should be bubbled through concentrated sulfuric acid in a wash bottle or anhydrous calcium chloride or calcium oxide in a U-tube. dry the gas, because these are drying agents. So next we are going to go to the collection of the gas. So now we have dried the oxygen gas. So how are we collecting the dry oxygen gas? We are saying dry oxygen is collected by either upward delivery tube, and the reason why we are collecting oxygen by upward delivery tube is that it is less denser than air. Or what we can do is we can collect the dried oxygen by the use of a syringe, since it has almost the same density as that of air. So let's see those setup that shows how oxygen is dried and collected. So in this method, we're having potassium chlorate 5. When it is heated, we are going to get oxygen gas. So the oxygen gas is dried using concentrated sulfurous acid in a wash bottle, which is a drying agent, and the dry oxygen is collected by the use of a gas syringe or syringe. So we go again, see the other one, it is here. Here we are having catalytic decomposition of hydrogen peroxide by the manganese peroxide, and the oxygen gas goes through the delivery tube, where it is going to be dried by the use of anhydrous calcium chloride or calcium oxide in a U-tube, and the dried gas is collected by upward delivery tube because oxygen is less denser than air. So next, let's proceed to the physical properties of oxygen gas, and here we are saying oxygen has several physical properties. One of them we can talk about, it is color. It's colorless and odorless gas. So that means oxygen has no odor or has no smell. So next, number 2, we are saying it is slightly soluble in water. That's why it's collected by our water method. It is less denser than air. That's why we were collecting by upward delivery tube. It has a boiling point of negative 183 degrees Celsius, and we are saying it has a density of 1.43 gram per liter at standard temperature and pressure STB. So that is the end of our lesson today. Thank you.